So the goal of Chapter 4 is to be able to, given an equation of a function, and let's say a continuous function, one whose graph has no breaks, use derivatives to help you draw the graph of that function without using a graphing calculator and without plotting a bunch of points. We need to make one observation. Look at this graph. Notice there's some key or critical points. If I just knew these turning points, if I just knew the coordinates of these turning points, wouldn't that give me a lot of information about this graph? I could just connect the dots, right? I know there would be a question about the shape of the graph, but we know the second derivative is going to tell us the shape of the graph, right? If the second derivative was 0 over a portion of the graph, the shape would be linear. If the second derivative was positive, it would be concave up. If the second derivative was negative, the shape would be concave down. Okay? But finding these turning points is just critical. Notice one thing. At every one of these turning points, there's either what? A horizontal tangent line, so the derivative would be 0, or what happens? There's a sharp corner. Therefore, where the derivative is undefined. But there's a horizontal tangent or a sharp corner at every one of these turning points. If you look on page 280, section 4.1, a critical number, here's the definition, a critical number of a function f is a number c in the domain of f. In other words, there's got to be a point on the graph, CF of C. There can't be a hole there. Such that either the f prime of C, the derivative evaluated at C, is 0, or the derivative evaluated at C, f prime of C, does not exist or is undefined. So critical numbers are x-coordinates of points on the graph of a function where there's either a horizontal tangent line or there's a sharp corner. When we have an equation in just a minute of a function and we want to draw a graph without the calculator, it's going to be essential that we go fishing for these critical points. We go looking for places where the derivative is 0 or undefined. And they'll give us these key points. It's just like connecting the dots and getting the shape right with the second derivative. The first derivative, tells increasing, decreasing behavior. But if we have the points, if I'm going from this point right here, see where the arrow to this point, I know I have to decrease, right? Okay, we'll look at an example in just a minute.